Welcome back to our lecture series on nanostructured materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the last lecture, we explored how scaling laws affect mechanics, looking at concepts like surface to volume ratio, strength to weight relationships, and even why fleas can jump so high compared to elephants. Today in lecture 3, we turn our attention to scaling laws in electrical systems. Here we will see how reducing size not only changes mechanical behavior but also dramatically alters electrical behavior, shaping the future of nanoelectronics and advanced technologies. As we begin exploring scaling in electrical systems, it is important to note that at the nanoscale, electrostatics rule. When objects become extremely small, electric fields become the dominant forces. They act as powerful tools for positioning, orienting, and even assembling nanoparticles with high precision. At these tiny scales, electrostatic interactions dominate over gravity and inertia, which are practically negligible. This has enormous implications for applications from assembling nanoparticles to developing nanoelectronic devices to fabricating micro and nanoscale actuators and sensors, and even nanosensors for detecting tiny changes in the environment. In other words, mastering electrostatics at nanoscale is key to unlocking the next generation of nano devices and technologies. Now, let us see why is learning about electrostatic field strength so important at the nanoscale. We can think of it in terms of the acronym SCAN. First, sensors. Electric fields enable nanoscale detection and actuation, making them central to nanosensors and MEMS devices. Second, charge transport. Electrostatics guide how charges move through nanoscale devices and semiconductor, which is fundamental for electronics. Third, assembly. External fields can be used to position and orient nanoparticles with remarkable precision, almost like using invisible tweezers at the nanoscale. And finally, nanoelectronics. Electrostatics directly impact capacitance, charge distribution, and even quantum effects in nanoscale electronic components. So, mastering electrostatic field strength is not just a theoretical concept, it is a cornerstone of how we design, build, and operate nanoscale systems. Let us now look at the electrostatic field strength in more detail. The electric field strength, written as ES equal to V divided by D, depends on the characteristic length D over which the voltage is applied. The key point is that the electric field is inversely proportional to distance. If we shrink the separation D while keeping the same voltage, the field strength increases dramatically. This means that as the devices get smaller and smaller, the same applied voltage produces much stronger fields at the nanoscale. That is why electrostatics dominates when we go down to tiny dimensions. Transistors are the most fundamental building blocks of modern CMOS-based electronic devices. Here you see a schematic of a field effect transistor. It has three main terminals: the source, the drain, and the gate. When a voltage is applied at the gate, it creates an electric field that controls the flow of current between the source and the drain. In simple terms, the transistor acts like a switch. Current either flows, representing a digit 1, or it does not flow, representing a digit 0. Billions of these tiny switches are packed together on a single chip, forming the logic circuit that powers computers, smartphones, and nearly all of the electronic devices that we use now. As you see in the schematic of the transistor that I just discussed, it looks quite big and easy to follow, but in reality a transistor is extremely small. Here on the left is a 1 by 1 inch microchip, and inside it are billions of these transistors packed together. They are made so tiny that we can fit an astonishing number of them into a single chip. So while the schematic helps us understand the concept, in practice these devices are microscopic and billions of them working together are what make our modern electronic possible. This brings us to Moore's law. Back in 1965, Gordon Moore, the co-founder of Intel, made a famous prediction: the number of transistors on a chip would roughly double every 2 years. Here on the chart you can see how transistor counts have grown from just a few thousand in 1970s to billions in modern processors. This exceptional increase has been the driving force behind the rapid growth of computing power over the past 5 decades. Moore's law has not just been a prediction, it has acted as a roadmap for the semiconductor industry, pushing engineers to continuously shrink device sizes, improve manufacturing, and pack more functionality into each generation of chips. Now, let us see what an actual transistor looks like under an electron microscope. If you were to take a computer from around 2007 or 2008, open it up, remove the chip, and zoom in with a transmission electron microscope, you might see something like this. This is an example from the 45 nanometer manufacturing node, the technology level used at that time. 45 nanometer here refers to the gate length of the transistor, and it was cutting edge back then. Chips at this scale powered everything from laptops to early smartphones. At this size, however, traditional silicon dioxide gates could no longer handle the job because leakage currents became too high. To overcome this, the industry introduced high-K dielectric materials along with metal gates. This innovation allowed transistors to stay small while maintaining performance and reducing leakage. It was a major milestone, proof that new materials had to be introduced to keep Moore's law moving forward. This chart shows the remarkable journey of CMOS technology scaling over the last few decades. Back in the late 1990s, transistor sizes were in the range of 250 to 180 nanometers. By the mid-2000s, we had reached the 90 and 45 nanometer nodes, like the one I just showed you under the microscope. From there, scaling continued rapidly: 32 nanometers, 22 nanometers, then 14 and 10 nanometers. Today, the most advanced chips are produced at 3 nanometers, and industry roadmaps are already pushing towards the 2 nanometer node. Notice how this progression is plotted on a logarithmic scale. Each step down represents a massive leap in technology, materials, and manufacturing. What is most striking is that the relentless scaling has not only made devices faster and more energy efficient, but has also required new materials, new architectures, and entirely new fabrication methods at every generation. As we continue shrinking transistors down to nanometer dimensions, new problems start to appear. One of the most severe challenges is known as the short channel effect. In a MOSFET, the gate is supposed to control the flow of current between the source and drain. But when the channel length becomes too short, the electric field from the drain begins to interfere with the gate's control. This causes leakage current, poor switching, and loss of reliability. To avoid this, device designers use what is called a natural length, represented by the symbol lambda. For a transistor to work properly, the gate length should be at least 6 times larger than this natural length. In simple terms, if we shrink too aggressively without respecting this scaling limit, transistors can no longer behave like a proper switch. That is why the short channel effect is one of the biggest roadblocks in further miniaturization. So far, we have been focusing on transistors themselves, the fundamental switches of modern electronics. But as the number of transistors on a chip keeps increasing, thanks to Moore's law, another critical factor comes into play: the interconnects. These are the metal wires that connect billions of transistors together, allowing them to communicate. And just like transistors, interconnects also face their own scaling challenges. Let us consider resistance. The resistance of a conductor is given by the expression R equals rho d over A. For a cube, the cross-sectional area scales as d squared, which means resistance scales inversely with size 1 over d. This tells us that as we make conductors smaller, their resistance increases. For example, a road block that is 1 centimeter in size has a resistance of just a few microohms. But if we shrink that block down to just 10 nanometers, its resistance jumps to a few ohms. This dramatic increase in resistance at a small scale makes interconnect performance another challenge in modern nanoelectronics. Before we proceed further, let us pause for a quick problem to make our understanding more firm. Question is, what is the resistance of a cubic micrometer of copper given rho equal to 17.2 into 10 to power minus 9 ohm meter? How much more or less resistance does a cubic micrometer of copper have compared with a cubic millimeter? Take a minute to think it through. This ties the scaling law for resistance directly to a real interconnect metal like copper. You can write your answers in the comments or email them to me. Let us now look at how scaling affects current and power. From Ohm's law, current equals voltage divided by resistance. Since resistance scales as 1 over d, current itself scales linearly with d. This means that if we apply the same voltage, larger conductors can carry proportionally more current. But we should add a caution here. In very large electric fields, Ohm's law can start to break down. For example, if we place 10 volts across a gap of just 2 micrometers, the field strength becomes 5 million volts per meter. At this level, even the resistivity of the material may vary with the field. Now, what about power? According to Joule's law, the power generated is resistance times current squared. If we substitute the scaling relations, we find that the power generated also scales with d. So smaller systems generate less total power. However, here is the catch. The mass and heat capacity of the device scales as d cube, which decreases much faster. This means that although smaller devices generate less heat overall, they also heat up much more quickly because they have so little heat capacity to absorb energy. So the key takeaway is the power generation scales down with size, but temperature rise becomes more severe, and that is why heat management in these systems is one of the biggest challenges. Now let us look at how capacitance scales with size. For a parallel plate capacitor, capacitance C is given by epsilon naught times epsilon R times the plate area A divided by the separation D. If we assume square plates, then the square area scales as d square, while the separation D also scales with d. Putting these together, capacitance turns out to be directly proportional to d. In simple terms, larger capacitors store more charge at the same voltage because their capacitance increases with size. So the key takeaway here is bigger size d means higher capacitance. This scaling is extremely important in nanoelectronics, where reducing dimensions decreases capacitance and directly affects circuit performance and speed. Now that we have seen how capacitance scales, let us make a step back and ask, why are capacitors so important? First, in MEMS, actuators and sensors, capacitive sensing is the heart of many everyday technologies, from accelerometers and gyroscopes in our phones to touch screens and precision instruments. Second, capacitors play a vital role in energy storage and release. They can store charge and deliver it almost instantly, which is why they are used in camera flashes or to power MEMS devices during quick bursts of activity. Third, capacitors are essential for filtering and signal conditioning. They smooth out noise and stabilize power supplies, ensuring circuits run reliably. And finally, Capacitors enable timing and oscillation. In MEMS oscillators, for example, they help generate precise frequencies and keep circuits asynchronized. So capacitors are not just passive components, they are indispensable in powering, stabilizing, and timing the nanoscale world of electronics. Electrostatic forces are extremely important at small scales, especially for actuation in nanoscale and microscale devices. Now let us look at the case of parallel plates. The electrostatic force between capacitor plates is slightly special because the maximum voltage we can safely apply depends on the gap between the plates. This is connected to what is known as the Paschen effect, which describes how breakdown voltage varies with distance. For simplicity, we will assume the maximum safe voltage is proportional to the plate spacing d. With that, the electrostatic force expression can be written as proportional to d square. So here is the key point. As we make the system larger, the electrostatic force between the plates increases with the square of the size. Conversely, when we shrink things down, the forces fall off very quickly, which is why at nanoscale, we must carefully engineer fields and geometries to generate sufficient actuation. Before we move further, let us pause and think through a design problem. Suppose you are designing an electrostatic actuator made from parallel plates. You have two options. You could either double the plate area or you could have the separation distance half. Which of these do you think provides a greater improvement in the electrostatic force? Again, take a moment to work it out. You can share your answers in the comments below, or if you would like, send to me via email. Now, let us look at the electromagnetic actuation in MEMS and how magnetic forces scale. Electromagnetic actuators in MEMS are used to move tiny parts like beams, plates, or diaphragms. They work by using a magnetic field that interacts with a current carrying element, producing a force on the movable part. The position of that part affects the system's inductance. The magnetic force can be written as F magnetic equal to 1/2 I squared times dl by dx, where I is the current and L is the inductance. Now here is the scaling challenge. For the same applied voltage and material current, I scales with size d. That means I squared scales with d squared, and therefore magnetic forces also scales with d squared. The key takeaway is that if you shrink a MEMS electromagnetic actuator by a factor of 10, the magnetic force is reduced by a factor of 100. This sharp reduction in force is a major hurdle when we try to miniaturize electromagnetic system. Now I want to bring your attention to another phenomenon that poses a serious challenge as we continue to miniaturize devices: electromigration in metal conductors. Electromigration occurs when high current densities cause electrons to collide with metal atoms, slowly pushing those atoms along the conductor. Over time, this atomic drift can create voids, which leads to open circuits, or halogens, which can short neighboring lines. The impact is severe. Electromigration increases resistance and reduces the reliability of interconnects, and this challenge only becomes more critical as devices shrink and interconnects are packed over more density. In other words, even if we manage to scale transistors perfectly, the wiring that connects them can become the weak link in the system. This concludes lecture 3, where we examined how scaling laws shape electrical systems, from resistance and capacitance to electrostatics, transistors, and the challenges of miniaturization like short channel effect and electromigration. In our next lecture, lecture 4, we will shift our attention to scaling laws in optics and heat transfer. We will explore how light interacts with materials at small scales and how heat generation and dissipation becomes critical as devices shrink. These ideas are not only fundamental for nanotechnology, but also directly impact fields like photonics energy devices, and thermal management in electronics.